In the present part of the lesson, Electrostatics Part 2, we will be studying about the force between the charges. We know that the like charges repel each other and unlike charges attract. The magnitude of the force is given by Coulomb's law, according to which if you have two charges Q1 and Q2 separated by a distance r, the force of attraction or repulsion between the charges is proportional to product of their magnitudes and inversely proportional to square of the distance between them. Combining these two parts of the law, we get F proportional to Q1 Q2 over R square, or introducing a constant for vacuum, F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. Vectorially, we can write force on Q1 due to Q2 as F12, and here we make use of an assumption that all charges are positive. Q1, Q2 both are positive charges, so the expected force is a repulsive force. F12 denotes force on Q1 due to Q2. So this force will act towards left because it is a repulsive force. 2 to 1, it will act from Q2 to Q1. So the force is given by 1 over 4 pi epsilon naught Q1 Q2 over R square into this unit vector directed from second charge to the first charge. Similarly, force on Q2 due to Q1 will be towards right, that is from 1 to 2 or along R12, which we can write here as 1 over 4 pi epsilon naught Q1 Q2 over R square into the unit vector R12, which gives the direction. Now in terms of position vectors of the charges, supposing Q1 has a position vector R1 and Q2 has a position vector R2, then we can write by triangle law OA plus AB, that is R1 plus R12 equal to OB, that is R1 plus AB equal to R2, or R12 equal to R2 minus R1. And R12 cap means in this direction, it will be R2 minus R1 divided by magnitude of R2 minus R1. So we can write force on 1 due to 2, force on Q1 due to Q2, it will be in this direction, that is opposite to this. So we can write it as 1 over 4 pi epsilon naught Q1 Q2 over R2 minus R1 square along BA, B to A. Again the charges are assumed positive, equal to Q1 Q2 over 4 pi epsilon naught into R1 minus R2, that is vector along this direction, over R2 minus R1 cube. Here the unit vector is replaced by vector R1 minus R2 over its magnitude, giving you cube instead of square here. Similarly, F21 can be written as Q1 Q2 over 4 pi epsilon naught into R2 minus R1 because it will be towards Q2. R2 minus R1 over R2 minus R1 cube. Now, if you compare these two vector notations, you will find that F21 is equal to minus of F12. That is, the law is compatible with third law of motion, reaction equal to negative of action. So Coulomb's law gives force between two charges as F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square in vacuum, where this constant 1 over 4 pi epsilon naught is 9 into 10 to the power 9 Newton meter square per Coulomb square. This constant epsilon naught is called electrical permittivity of free space, and its value is given by 8.85 into 10 to the power minus 12 per Newton per meter square Coulomb square. The force between two charges placed a certain distance apart is also affected by nature of the medium in which the charges are placed. The force is modified by a factor k, that is, the force in a medium becomes 1 over k into 1 over 4 pi epsilon naught q1 q2 over r square, where k is called dielectric constant. The term k is sometimes also written as epsilon naught, epsilon r, the relative permittivity of the medium. So this constant k, that is dielectric constant or relative permittivity of the medium, is the ratio of the force between two charges in vacuum to the force between the same charges in the medium placed same distance apart. For example, the force in water is 1 over 80 times the force in vacuum. The force is weakened in the medium. The law, Coulomb's law, helps us define SI unit of electric charge, which is known as Coulomb after the scientist who has given us this law. If we take the charges, each of the pair of the charges as 1 Coulomb, and the separation between them is 1 meter in vacuum, then using this relation, force will come out to be 1 over 4 pi epsilon naught in vacuum equal to 9 into 10 to the power 9 Newton. So you can define 1 Coulomb as the charge which, when placed 1 meter apart away from an equal and similar charge in vacuum, repels it with a force of 9 into 10 to the power 9 Newton. Remember, Coulomb is a very large unit of charge. It is impossible to get a charge of 1 Coulomb on a single object. The submultiples are used as smaller units. For example, millicoulomb is 10 to the power minus 3 Coulomb, microcoulomb as 10 to the power minus 6 Coulomb, nanocoulomb as 10 to the power minus 9 Coulomb, and the charge on the electron, which is the smallest possible charge of independent existence, is 1.6 into 10 to the power minus 19 Coulomb. Here in this relation, if both charges are similar, both positive, both negative, the product will come out to be positive. And the force we know between similar charges is repulsive. So positive force signifies repulsion and negative force signifies attraction. Now, some applications of Coulomb's law. If we analyze this relation carefully, we have F inversely proportional to R. So if you plot a graph between force and R, it will be a curve. And since F is directly proportional to 1 over R square, a graph between F and 1 over R square will be linear or a straight line. Now see this question 3 for an application of this law. Two charges placed a certain distance apart exert a force F on each other. How will the force change if each of the charges and the separation between them is doubled? Now, if you use this relation gives us the force. According to the problem, if Q1 is doubled and Q2 is doubled, the numerator becomes 4 times. And if R is also doubled, the denominator also becomes 4 times, and hence the force between the charges will remain unaffected, that is F. Continuing with some more problems based on Coulomb's law, let's consider this question. Two charges 4q and q are placed at distance a apart. Where should a third charge small q be placed between them for it to be in equilibrium? Is the equilibrium stable? The situation in the problem can be represented diagrammatically as charge plus 4q at A and capital Q at B. Let us suppose that the third charge small q is placed at point C on the line joining A and B. According to the problem, small q charge at C is to be in equilibrium. That is, the net force on this charge should be 0, or the force on C due to A should be equal and opposite to the force on C due to B. That is FCA equal to FCB. Using Coulomb's law, you get 1 over 4 pi epsilon naught Q 4Q over x square equal to 1 over 4 pi epsilon naught Q capital Q over A minus x square, which implies 4 over x square equal to 1 over A minus x whole square, cancelling out the common terms. Now you can take square root of this expression. 1 over, that is 2 over x equal to 1 over A minus x, or x equal to 2A by 3. Now to find out whether the equilibrium is stable or unstable, if the charge small q is displaced slightly towards right, the force due to A will decrease and that due to B will increase. So it will experience a net
force towards left,
which will tend to restore its position. Hence the equilibrium is stable one. Now a slightly different question, question number 5. Two charges 4q and q are placed a distance A apart. Where should a third charge q be placed between them for the system to be in equilibrium? What should be the sign and magnitude of q? Here the difference is we wanted the charge q to be in equilibrium. Here we want the system to be in equilibrium. So force on each of the three charges in this case has to be 0. Now as in question 4, you can find the location of the charge to be placed between them, that is, it will give you x is equal to 2A by 3. For the system to be in equilibrium, we have an additional condition: net force on A equal to force on B equal to force on C equal to 0, or the force on A due to C should be equal and opposite of the force on A due to B, which implies force on A due to B equal to minus of force on A due to C. Using Coulomb's law, you get this relation: 1 over 4 pi epsilon naught q into 4q over A square equal to minus of 1 over 4 pi epsilon naught q 4q over 2A by 3 whole square. Again, cancelling out the common terms, you are left with q equal to q over 4 by 9, or capital Q equal to minus 9 by 4q. That is, the charge small q should be minus of 4 by 9 q. So this charge at center has to be opposite to each of the two charges, and the magnitude is given by 4 by 9 q. Now let's study a situation where we have more than two forces, that is, force amongst many charges. Here we need to apply the principle of superposition. In the diagram we have a large number of charges, q1 with position vector r1, q2 with position vector r2, q3 with position vector r3, and qn with position vector rn. Similarly, we have other charges q4, q5, q6 and so on. The net force on charge q1, if we write it as F1, is given by vector sum of the force on q1 due to q2, on q1 due to q3, on q1 due to q4 and so on. That is F1 net is equal to F12 plus F13 plus F14 and so on up to F1n. You have to take the vector sum because these are the forces. The general expression for force on any of the charges, say ith charge, can be written as Fi equal to sigma Fij. I is fixed, j varies from 1 to n, but j should not be equal to I for obvious reasons. To illustrate this principle and its application, let's take two examples. We have a system of three charges here. Charge on A is 9 microcoulomb, charge on O is 1 microcoulomb, charge on B is 16 microcoulomb. The distances marked here are in meters, 1, 2, 3, and this is 4 meters. What is the magnitude of net force on charge at O? Here for solution we have to find force on charge at O due to A, force on charge at O due to B. F1 denotes the force on O due to A and is given by 1 over 4 pi epsilon naught charge at O into charge at A over OA square, that is 9 into 10 to the power 9 into 1 microcoulomb charge, that is 10 to the power minus 6 into 9 microcoulomb, 9 into 10 to the power minus 6 over the distance 3 square. The force comes out to be 9 into 10 to the power minus 3 Newton along OP because it's a repulsive force. Similarly, you can find force on O due to charge at B, which comes out to be 9 into 10 to the power minus 3 Newton along OQ. Again the force is repulsive. Now the net force is F, and since we are interested in magnitude, it is given by the magnitude of the resultant of the two forces. The two forces being perpendicular to each other, you can use Pythagoras theorem, that is F, the net force will be F1 square plus F2 square whole root, that is 9 root 2 into 10 to the power minus 3 Newton. If you need to calculate the direction, it's very simple. The forces are equal, so the resultant will act midway between them, that it will bisect the angle between the forces F1 and F2. So this angle will be 45 degree. The resultant will make an angle of 45 degree with minus x or minus y directions. Likewise, we can take another example. Charges of 2 microcoulomb each are placed at the corners of a square with each side 3 meter. Calculate the net force on the charge at D. Here, the charge at D will experience three forces: due to A, due to B, due to C. Let's term the forces as F1, F2 and F3 respectively. You can find out force F1 as force on D due to charge at A equal to 1 over 4 pi epsilon naught QD QA over AD square, 9 into 10 to the power 9 into 2 microcoulomb into 2 microcoulomb over 3 square, the distance square. This 9 will cancel out here and the net force will be 4 into 10 to the power minus 3 Newton along dP, since it is a repulsive force. Similarly, force F2. F2 is force on D due to charge at B. The charges are same, but the distance is equal to the diagonal, which will be 3 root 2. 3 square plus 3 square root 3 root 2. So you can use the law, Coulomb's law, to get the magnitude of the force, which comes out to be 2 into 10 to the power minus 3 Newton along dr, d to r. Similarly, F3 numerically will be equal to F1, 4 into 10 to the power minus 3 along dq upwards. Now F1 and F3 are perpendicular to each other. So the resultant is given by Pythagoras theorem. Let's term it as F dash is equal to square root of F1 square plus F3 square, which will mean 4 root 2 into 10 to the power minus 3 Newton along dr. For net force on this charge, we have to add F dash and F2 because they are in same direction. So the net force will be F dash plus F2 equal to 4 root 2 plus 2 into 10 to the power minus 3 Newton along dr. It will be worthwhile to try a large number of other problems in order to grasp the subject matter and the content properly.